Hello, this is a lecture series for Chemical Engineering Thermodynamics I. We are at lecture 5A, which is the last part for this lecture series. We mentioned lecture 5A very often when we were in lecture 2 and lecture 4, and during that time I mentioned that some certain equations were used and were used without derivation, and it will be derived within this lecture. Just the introduction for relationship between parameters in thermodynamics. If you classify thermodynamics properties into several groups, we can do it in many ways, just like what we mentioned in lecture 1. But in this lecture, we will divide it into categories like this. The first group of parameters is called measure properties. Basically is whatever we can measure directly. Then another group is called fundamental properties, which were derived from thermodynamics law. And then lastly, we call this one derived properties, which were derived based on the convenience of applications. Again, the very first one is directly accessible. We can measure directly like temperature, pressure, and volume. The second one is resolved from thermodynamics law, like the first law and second law. And the third one is defined based on the convenience of our application. In addition to pressure, volume, and temperature, the other variable that can be measured directly is concentration. We don't mention concentration quite often in Thermo 1 because we assume the system to contain one single species. But if you move on to thermodynamics 2, which consider properties of mixture, then concentration should be another important parameter, and it is the one that we can take a sample from the system and measure its concentration by doing chemistry laboratory. For the second group, fundamental properties, when we discussed the first law in lecture 2, the first law introduced one parameter called internal energy. During that time, we said that the total energy of the system can be divided into three groups: kinetic energy, potential energy, and the rest is called internal energy. Right? Then in lecture 4, we introduced the parameters called entropy. The parameter itself was derived based on Carnot cycles to get ds equal to q over t, but the heat itself must be reversible heat. I also mentioned that according to statistical thermodynamics, entropy can be thought of as an indicator for chaotic dispersion of mass and energy within the system. For the third group, when we were in lecture 2, we derived enthalpy for our convenience. There are two cases for convenience of enthalpy derivation or enthalpy definition. The first one is in closed system. We define enthalpy change of the closed system under constant pressure to be equal to heat transfer into the system. That's one convenience. The other one is in open system. We define enthalpy so that we can combine the flow work to internal energy to get enthalpy, and therefore the work calculated from the first law in open system can be directly related to shaft work. We don't have to worry about flow work in the open system anymore. In lecture 4, we said that the second law of thermodynamics determines spontaneity of the system. In order to determine whether the system or the process is spontaneous or not, we need to consider both entropy change of the system and entropy change of the surrounding, so that when delta S of the universe is greater than 0, then the process is spontaneous. And normally it is not convenient to always consider the change of entropy of the surrounding. But for some cases, like when the system takes place under constant temperature and pressure, if you calculate delta G or change in Gibbs free energy of the system only, that is enough to determine whether the process is spontaneous or not. Okay, so during that time, Gibbs free energy was defined for our convenience to determine whether the process is spontaneous or not. In a similar manner, Helmholtz energy was defined as well. Okay, so this kind of thing or these kind of variables are considered as derived properties. The point is, normally the law of thermodynamics or the calculation was mainly focused on the variables which are not directly measurable. In first law, we talk about internal energy and enthalpy. In the second law, we talk about entropy and Gibbs free energy. None of that can be directly measured. So in order to make a connection to what we can measure, we need to find the relationship between whatever we use in the law of thermodynamics to whatever we can measure. This line here, or this relationship, is called thermodynamics network. So in order to convert the variables in thermodynamics law to parameters that we can measure, we need relationship among them. This relationship is called thermodynamic network, and this is the focus of this lecture. The very first relationship among variables is called fundamental relations. The very first one for the fundamental relation was derived based on the combination of the first and the second law of thermodynamics. From the first law, we define the change in internal energy, the total change in total internal energy. In this case, I use UT here. This is extensive properties. UT has unit in joule. Okay, this is the by definition of the first law. It is the heat transfer from the system or into the system plus the work into or out of the system. Okay, again, Q and W here supposed to have unit in joule. The whole equation here was written as extensive properties. If I like to change from total internal energy to internal energy per mole within the system, I just get UT equal to NU. And for closed system, the number of mole in the system is constant. I can take it out from differentiation. Okay. This particular equation can be written for any kind of path, any kind of change, because this is universal. It is first law. It is always true. For this particular system, if I pick the process to be reversible, then reversible work can be defined based on minus P dV. But in this case, W is total work. So V here supposed to be total volume. Okay? So if I convert total volume into molar volume, I get NV. So differentiation of NV times together. But N in this case is constant. For closed system, I can take N out. Okay? For reversible process, according to the second law, we can make relationship between reversible heat and entropy. According to the definition of entropy change, ds would equal to Q reversible over T. So if you rearrange the equation, you get Q reversible equal to T ds. And in this case, since Q is total heat transfer, so differentiation here is supposed to be d of the total entropy. Again, you can change total entropy into molar entropy by multiplying it with N. For closed system, N is constant. We can take N out of the differentiation. So if we replace W here and Q here into the first law and take N out of the differentiation from the right hand side, the number of mole within the system from the left hand side and right hand side can be cancelled out. You will end up with this equation. Okay? If you notice this blue equation, even though it was derived based on reversible path, but at the end, all parameters within this equation are all state properties. So therefore, the equation itself is considered as a universal equation. It can be used for any kind of path, any kind of change, any kind of process, any kind of system. Okay, because they all are state properties. This is what we call fundamental relation. If I start from this fundamental relation and then use the definition of enthalpy, in lecture 2, enthalpy was defined as internal energy plus product of pressure and volume. If you take derivative, the product of pressure and volume can be differentiated into VdP plus PdV. The first two terms here are the same as what we derive over here. So, if we use the first fundamental relation and then expand this du into TdS minus PdV, you see that the red PdV here and PdV over there would cancel out, and at the end you gain another relationship containing enthalpy, entropy, and PVT. Okay, this is another fundamental relation. Similarly, if we start with definition of Gibbs free energy, according to lecture 4, we get G equal to H minus Ts. If you take the derivative of the equation, differentiation of T times S would equal to TdS and SdT. Okay, but dH here, according to this fundamental relation, can be expanded into TdS and VdP, and these two terms cancel out, and at the end you get another fundamental relation. This one is the third one, dG equal to VdP subtracted by SdT. And lastly, from definition of Helmholtz energy from lecture 4, A equal to U minus Ts. If we repeat the process, take derivative and replace du here using the first fundamental relation, TdS in this term and TdS in that term would cancel out, and at the end you get the last fundamental relation. These four equations are very important, that they're used for derivation of relationship among thermodynamics parameters. So if I consider the first fundamental relation and then divide the variables into red group and green group, okay? In this case, if I take the system to be constant volume, okay, if you consider this green variable V here, if I consider the system with constant volume, then dV here should be 0. Okay, if it is 0, then you can take ds to the left hand side to get partial differentiation of u with respect to s under the condition of constant volume to be temperature only. So from this fundamental relation, if you restrict the system to constant volume and rearrange the equation, you obtain this relationship. In similar manner, if you change from constant volume to constant entropy, keep ds here to be constant, so ds becomes 0, and then move dv to the left hand side, you will obtain another relationship, du by dv at constant entropy to be minus pressure. Okay, these two are considered as what we call the first derivative of fundamental relation. Again, if you repeat the process for the second and third and fourth equation, you will obtain a pair of equations for each fundamental relation like this. I believe you can do it by yourself. Okay? Then, from the first derivative of fundamental relation, if I take this blue equation, okay, and I take another derivative, this time, if I take derivative of this blue term with respect to volume at at constant entropy, then just like this, on the left hand side, the blue terms is this term. I take derivative with respect to volume at constant entropy. If I do this on the left hand side, the right hand side must be done as well. So derivative of the right hand side, which is the temperature here, derivative with respect to volume under constant entropy. Okay, then if I consider the red equation, this red equation here, if I take derivative with respect to entropy at constant volume, the left hand side would be this term, while the right hand side under the same thing, you can get dP by ds at constant volume like this. And according to calculus, differentiation with respect to x first and then differentiation with respect to y later should equal to the differentiation with respect to y first and then differentiate with respect to x later. Therefore, the left hand side, this term and that term are essentially the same. You can move v into inside and move s out. They are essentially the same. Therefore, you can get the right hand side, these two terms are equal. You get this equation. Okay? So if you take these two pairs, and repeat the process, you take another derivative, the second order derivative, and make sure that after you do that, the left hand side are equal. Then you can get another relationship here from the second, the third, and the fourth equation. These four relationships are called Maxwell equations. Maxwell equation will be used very extensively when we derive the relationship amongst thermodynamic parameters. Now let me show you how to use Maxwell equation to derive the relationship among thermodynamics parameters. The first application is the calculation of delta U. As in lecture 2, we said for the system with degree freedom of 2, we can pick two variables to represent internal energy, and normally for internal energy we would prefer to write it as a function of temperature and volume. From calculus, if you take derivative of du, then on the right hand side you can write it as a differentiation of two terms combined, one with respect to dt and one with respect to dv. Okay, this is just basic calculus. The first term on the left hand side, this term was defined to be heat capacity at constant volume. No problem about the red term. The right term, this is U itself is not measurable, so we would prefer to convert internal energy here to something that we can measure. How can we do that? We want du by dv. If you look at fundamental relationship here, you can see that this equation contains du and dv. So I'm going to start with this equation. Then if I divide the whole equation by dv so that I can obtain du by dv like this, and restrict the differentiation to be at constant temperature, just like this here. Then from the fundamental relation, on the left hand side you get du by dv with respect at constant temperature like we want. On the right hand side, if you repeat the process, divide everything by dv and restrict it to constant temperature. The first term here you get ds by dv at constant temperature, where the second term dv over dv becomes 1. You get minus p. Okay, so this term is essentially that term. However, still we still get stuck with entropy here. So we need to convert this entropy to something measurable again. But lucky for us, if you look at the Maxwell equation, this particular term is this one. So according to Maxwell equation here, you can translate or you can relate this group to PVT, which are all measurable. So if you replace the equation over here and then plug it back to this term, you end up with familiar equation that I told you from lecture 2 that you can use this one, and I'm going to derive it for you in lecture 5a. Okay, so this is the derivation. The second application is calculation of delta H. Again, from lecture 2 we can write enthalpy as a function of temperature or pressure under the system of degree freedom of 2. Using calculus to expand into two terms, the very first term was defined to be heat capacity at constant pressure, but the second term must be defined further so that we can convert enthalpy here to something measurable. Once again, we need enthalpy and pressure. If you look at fundamental relationship here, this particular equation contains enthalpy and pressure, so we will start with that. From this, if you divide the whole equation by dP and restrict the system to constant temperature so that we can obtain this term on the left hand side. On the right hand side, you repeat the process, you end up with partial differentiation of entropy with respect to pressure at constant temperature. The second term here, when you divide by dP, dP by dP becomes 1. So you end up with volume by itself. Okay. You might ask, or you might wonder, what would happen if instead of using this fundamental relation, if I start by using this equation instead? Can I solve to something useful? The answer would be no, unfortunately not. Because if you start with du on the left hand side and repeat the process, you will end up with du by dP at constant temperature, which cannot be related to something that we know. Unlike this differentiation here, dP by dt at constant temperature can be related to something here according to the Maxwell equation here. You can convert this into that part, right? And then replace this. Everything on the right hand side are measurable. But if you pick the first equation here, you end up with du by dP at constant temperature, which do not match the set of Maxwell equation that we have here. So that cannot translate whatever you have, entropy, enthalpy, into something measurable. So you might also ask, how do we know how to start? I would say that conventionally there are only delta H, delta U, and delta S. Okay, I'm going to show you all, and the derivation will follow what I'm going to show you here. So if I plug this term in here, you end up with again the familiar equation that I gave you in lecture 2, and I said that I'm going to show you the derivation in this lecture. For entropy, in lecture 4, I said there are two ways to represent entropy change. The first one is writing entropy as function of temperature and volume. If you expand using calculus, you get this term. And then these two terms require some derivation. Okay? We don't have definition relating to Cp and heat entropy directly, so we need derivation on both terms. Let's start with the first term here. We need ds, we need dt. Okay, so if I start with the first fundamental relation here and then divide the whole equation by dt and restrict it to constant volume, so that once you divide by dt and restrict to constant volume, this term becomes what we want. Okay, and then on the left hand side you got du with respect to dt at constant volume, which is Cv. It is heat capacity. Again, if you change this fundamental to something else, let's say you pick this equation, on the left hand side you get dH by dt as constant volume, which was not defined. Okay, so you have to start with this one so that you end up with something familiar. So the left hand side you get du by dt at constant volume, which is heat capacity, Cv. The right hand side here is what we want, and then this term, when you restrict to constant volume, dV here becomes 0, or you can say that when you restrict V here to become constant, dV here, the change under constant condition will become 0 by itself. This term will be neglected. Okay? So you can take this temperature as denominator under CV here and put it here, so you get CV over T dt. On the other hand, this term is basically was already written by Maxwell equation. So you can pick Maxwell equation here and replace it here. So when you combine, you get CV over T dt and differentiation of P dt at constant volume dV. Okay, this one was given to you in lecture 4. Alternatively, if you write entropy as function of temperature and pressure, you repeat the process, you end up with these two terms which are not known yet. We need derivation for these two terms. Okay, for the first term, I'm going to start with enthalpy, this fundamental relation, because we know we have ds here. If you divide by dt and restrict to pressure, on the left hand side you get dH by dt as constant pressure, which is heat capacity. We already defined for that. Okay, so you divide by dt, restrict it to constant pressure, the left hand side becomes dH by dt as constant pressure, which is heat capacity Cp. The first term on the right hand side, this is what we want to put it here. This term, when you restrict system pressure to be constant, then dP here becomes 0. Okay, you can also say that when this is constant, dP here is 0. You can drop this term. Okay, so this one is Cp. You can plug this back here to be Cp over T. The second term here is the same as written here in Maxwell equation. So you can move the minus sign here to the left hand side and put it here so that you get this equation. Again, this equation was given to you in lecture 4. So these are basic applications of Maxwell equation together with fundamental relation. Basically, we can use this one to calculate dH, du, and ds in many ways. Another application is about the calculation of Gibbs free energy. There's many occasions that you are required to calculate Gibbs free energy of the reaction at some temperature. If that temperature is not a conventional temperature, then sometimes you don't have the data. Okay, normally to calculate delta G, you can do either by using definition dG delta G equal to delta H minus T delta S. Okay, if you can have delta H and delta S of the reaction at that same temperature, then you can use this definition to find delta G of the reaction. Or you can also use Gibbs free energy of formation of the product subtracted by of the reactant. Then you can get delta G of reaction as well. But again, if you want delta G of reaction at the unconventional temperature, the Gibbs free energy of formation here must be at the same temperature that sometimes you cannot have the data. So if you don't have the data for entropy at the temperature of your interest, or Gibbs free energy of formation of the same thing, the temperature of your interest, then these two sometimes would be hard to be used directly. So we need to start from the temperature, standard temperature, and then move on to the temperature of interest. This is how we can do that. This is alternate way to do that. Okay. So if I start with differentiation of G over T with respect to temperature, by calculus you can see G over T is the same as G times 1 over T. And using the differentiation of products, you can expand this one to 1 over T dG plus G times differentiation of 1 over T, which is minus T 1 over T squared dG times G. Okay. Then earlier, from one of the first derivative of fundamental relation, we get this relationship. Okay, dG by dt is the same here, but this one is partial derivative at constant pressure. But Lucky for us, normally when we consider Gibbs free energy of reaction, this is considered as constant temperature and constant pressure. So if we restrict our pressure to be constant, then this differentiation can be written at constant temperature and pressure. Okay, and this term can be related to entropy according to this relationship. Okay, so we plug this, replace this one by minus S, so the equation ends up like this. Then, according to the definition of Gibbs free energy, G equal to H minus Ts. So you can combine these two terms together. If you multiply the numerator and denominator here by temperature, you get T squared underneath here, and you combine these two terms together, you get this combination, which is directly the same as enthalpy. Okay, from this, if we want to change dH here to something, dt here to something that is more convenient for derivation, let's start with definition or start with calculus. Let's say we have differentiation of 1 over t. According to calculus, that is minus 1 over t squared dt. Okay, you can rearrange the equation, so dt would equal to minus t squared times d1 over t, and plug it here. Okay, so on the left hand side you get d of the ratio g over t over d of 1 over t, and then on the right hand side this t squared and this t squared would cancel out. This minus sign and this minus sign would cancel out as well, leaving only enthalpy on the right hand side. Then if you take integration, you move this d of 1 over t to the right hand side and do the integration. You should notice that the left hand side, the term here is differentiation of something. The integration of this term is very simple, straightforward. Again, the right hand side, if you want to do integration, you need to know the function of enthalpy with respect to temperature first. Okay, now if we want to calculate delta G of reaction, we need to write this equation for product and reactant, and take the equation of the product subtracted by equation of reactant. The left hand side would turn G by itself to delta G of reaction. Okay, the right hand side, when you have enthalpy of the product subtracted by enthalpy of the reactant, you get heat of reaction on the left hand side. The temperature in the equation for reactant and temperature in the equation for the product, they are the same because we consider reaction at the same temperature. The temperature of the reactant and the product are the same, right? So T here are the same. You can take T out of the equation. Then from this equation, to do the integration, the left hand side can be integrated directly. The right hand side, on the other hand, if you want to do the integration, you need to know the relationship between heat of reaction with respect to temperature. But if you consider, or if you assume that the range of the temperature for this integration is not so large, the heat of reaction can be assumed to be constant. You can take heat of reaction here out of the integration and then leaving only 1 over t squared dt, which is straightforward for integration. What you have, the left hand side, you get delta G over T of the temperature 2 subtracted by the same thing of the temperature 1. Okay, if temperature 1 is standard temperature, let's say 25 degrees Celsius, which we have the data, that means delta G of reaction at T1 is known. Delta G of reaction at T2 is what we want to know. Then the integration on the right is straightforward to get 1 over T2 subtracted by 1 over T1, assuming that delta H of reaction is constant. Therefore, this equation is very useful to calculate delta G of reaction at temperature T2, knowing to calculate delta G of reaction at temperature T2, knowing delta G of reaction at temperature T1, and then assuming that heat reaction here is a heat reaction at the same temperature T1, okay, and assuming that this heat reaction is not a strong function of temperature. A little bit more about Gibbs free energy. In thermodynamics, if you move on to thermodynamics II, further derivation would be done based on Gibbs free energy. That's because in thermodynamics world, we consider Gibbs free energy as generating function. Okay, let me show you how. Let's start with relationship of Gibbs free energy over RT. If you take the differentiation dG over RT, basically you consider 1 over R is constant, you can take it out of the differentiation, right? And this is basically G times 1 over T. Differentiation of the product, you get 1 over T dG, and G times differentiation 1 over T, which is minus 1 over T squared dt, okay? The dG here, if we use fundamental relation, you can expand this dG into two terms. On the other hand, the Gibbs free energy here can be expanded using definition of Gibbs free energy itself. If you plug it in there, you can see that the S over RT here and here are cancelled out. At the end, you get two terms here, okay? From this, I'm going to do the same trick as what I did for the first derivative of fundamental relation. If I restrict the system to be constant temperature, this dt becomes 0. You can move dp here to the left hand side. You get d of the G over RT dp at constant temperature, okay? The other side of the equation is basically V over RT. Then I repeat the process, take the system to be constant pressure, and then this term will be dropped, and then remove this dt to the left hand side, writing another relationship. You get d of G over RT with respect to temperature at constant pressure to be equal to h over RT squared. You can move minus sign to be in front of this term, okay? Then move one of the temperature to the right hand side and start with the definition of Gibbs free energy, G equal to H minus Ts. If you rearrange the equation and divide the whole equation by RT, okay, this term becomes S over R. Rearrange this equation so that you can get entropy over R on the left hand side. The right hand side is this function, okay? Similarly, if you start with definition of enthalpy, you can rearrange this equation, divide the whole thing by RT, and move internal energy to the left hand side, move enthalpy to the right hand side. You end up with this equation. Why I'm doing this? Let's say if the relationship between Gibbs free energy and temperature pressure is known, if you can write equation for Gibbs free energy as a function of temperature and pressure, then G over RT is considered as known relationship. That means G over RT here and here are known, right? Once you know the function, then you can do differentiation. If you know how G over RT can be written as a function of temperature and pressure. If you do differentiation with respect to pressure at constant temperature, you can get this term, which is volume. If you repeat the differentiation, but this time differentiated with respect to temperature at constant pressure, then you get enthalpy, okay? Again, if this is known, and enthalpy here, which was previously calculated, the blue term here will be moved here. The right hand side are all known. That means you can calculate entropy. And when you put enthalpy here, PV over RT here is essentially a compressibility factor from lecture 3. Okay, this is known if you know the equation of state. That means you can calculate internal energy as well. So can you see that once the relationship of Gibbs free energy as a function of temperature and pressure is known, then you can find volume, enthalpy, entropy, internal energy are all defined. So that's why we call Gibbs free energy as generating function. Once you know Gibbs free energy, you can generate anything in thermodynamics. Okay, that's why it is very important. And from now on, when derivation for new variable was done, it is usually start with Gibbs free energy. Okay, so in this lecture, even though most of the lecture are heavily relying on derivation, but the main content of this lecture is about relationship among thermodynamics parameters. So we have several relationships, the fundamental relation and Maxwell relation, that can be applied to something further. Okay, the example that I show you was previously used in lecture 2, lecture 4. Okay, but you can do anything based on this relationship. For examples, you can derive heat capacity. Okay, normally we know heat capacity under the ideal gas assumption. If it is not ideal gas, then heat capacity at the back of the thermodynamics book is not applicable. Okay, in order to derive for heat capacity of non-ideal gas state, you have to start with heat capacity of ideal gas, then move on to the state of non-ideal gas. The move on like that requires relationship between heat capacity at one certain state with respect to another. Along the way, you need relationship of the thermodynamic properties. You may also need to find relationship between heat capacity CV and CP. What we learned from lecture 3 is CP equal to CV plus R. But that relationship is applicable only for ideal gas. If it is non-ideal gas, you need to derive and use this thermodynamics network. Okay, so this is what we thought of as a fundamental relation that we can apply to derive the variables that it is useful in the future. So this is it for the lecture 5A, and this is the last part of my thermodynamics lecture series. Thank you for watching.